Okay, let's get to the next problem here. So you have an engine in a small airplane is specified to have a torque of 60 Newton meters. The engine drives a 2-meter long 40 kilogram propeller. On startup, so it starts at omega equal to 0, it's not moving at all. How long does it take the propeller to reach 200 RPM? So let's draw a picture of what's going on and then do the problem. So the propeller looks something like this. They're usually like this, and you spin them. But let's model them. They're just it's like a rod. Here is a rod. And it will spin about its center of mass. So it will spin this way. This is the axis of rotation. It will just go like this and turn around it. So what's the moment of inertia of a rod about its center of mass? Because here they say how long, so it will accelerate. So we need to calculate the angular acceleration. So we're going to start with the fact that the net torque is equal to I alpha, and then calculate alpha from the torque, and I alpha would be tau divided by I. So I need to know I know the torque, but I don't know the moment of inertia. But the moment of inertia about the center of mass for a rod, if you remember, was 1/12 the mass of the rod times the length of the rod squared. So I have 1/12, and then it's a 2-meter long 40 kilogram propeller. So 2 meters, and then it's 40 ml squared. So the mass is 40 kilograms, and L is 2, and we need to square it. So I get the moment of inertia, I about the center of mass for a rod, will be approximately, let's write it down, 40 times 4, that's 160 over 12. That's about 40 over 3. 40 over 3 kilogram meters squared. I will leave the 3 there because when we divide the 60 newtons for torque, it will we'll get a nicer number. So we get alpha will be tau over I, and tau is 60 divided by 40 over 3. So that will be the 3 goes upstairs, so it becomes 180 divided by 40. 180 divided by 40, and that's 18 over 4, or 9 over 2, or 4.5 radians per second squared. That is alpha. Okay. And we would like to know how long will it take it to reach the 200 RPM. Well, first, we have omega initial is 0. We would like omega final to be 200 RPM. So omega final is 200 RPM. That's revolutions per minute. I need it in radians per second to be able to use this. So times 1 minute for every 60 seconds times 2 pi radians for every 1 rev, min. So I have radians per second. And so I get 200 times 2 pi over 60, and that gives me 200 times 2 times pi over 60. I got about 20.94. 20.94 radians per second. Okay. And I know that omega final is equal to omega initial plus alpha times the time. It's constant acceleration, constant angular acceleration. So the time will be omega final minus omega initial over alpha. Omega initial is 0, so it will just be the omega final, 20.94 divided by the alpha, which is 4.5. And we get this divided by 4.5. And that will give about 4.65 seconds. 4.65 seconds. So 4.7 seconds approximately. So our next example will involve a rope, a pulley, and something that is hanged on the rope, and then as the thing falls, the pulley starts to spin. So I'm going to write it down for you. Okay. So here is the next problem. Here you have a 2-kilogram bucket, and it's attached to a massless string. So the string is massless, it's ideal. And it's wrapped around a 1 kilogram, 4 centimeter in diameter cylinder as shown. So now you have a kind of a pulley, but the pulley now has mass. Remember, previously we assumed that the pulleys had no mass, but now they will. So as they spin, they do have a moment of inertia because their mass is not zero. You have this mass here, it starts at rest. As it falls, how long will it take it to drop by 1 meter? So the initial height is 1, the final height will be 0. So how long will it take it to go? As you may imagine, everything is at rest. As you release it, the mass falls and the string gets released and the pulley spins. And the pulley spins, as the pulley spins, the string or the rope unwinds and the mass falls. And what happens, the unwinding of the rope is corresponding to the angle by which it turns. And the acceleration of the mass as it falls has to equal to the tangential acceleration of the rope, so that the rope doesn't slip and it doesn't break and so on. So if this spins by an angle theta, the mass will fall by a length x, and if this is an angle theta, then this much rope is released and the mass falls by that much. And this much is delta S here, delta S. This is delta theta. And delta S is equal to R times delta theta, where R is the radius of this. So we know that delta S will equal to R times delta theta, and so delta S over delta t here will give me the velocity. That's the tangential velocity is equal to R times delta theta over delta t is omega. And we get the familiar R omega if the rope is released. And the acceleration is also, if you take derivative of this, you get the tangential acceleration. Derivative of omega is alpha, so you get R times alpha. So you have all of this, which we already kind of knew when we have motion with rotation, with something spinning, the relationship with the tangential acceleration and the tangential velocity to the angular acceleration, the angular velocity. So how long will it take it to fall to the floor? So first, let's write down Newton's second law for this mass, for the mass first. So for the mass m here, the forces on it are mg, and then there is the tension this way, and then it will accelerate this way. The acceleration is negative a. So we have the tension minus mg will equal to the mass times acceleration, which is negative a. And therefore the tension will equal to mg minus ma. All right. I have two unknowns. The mass is known. The mass is 2 kilograms. And I don't know the tension. I don't know the acceleration. I need to figure it out. Let's look at the pulley now. For the pulley, let's kind of zoom into it. The rope is here. That's where it loses touch. And why does the pulley spin? Well, the reason is it's spinning about its own axis. This is R. And there is a force down, tension pulls. So that's the force on it, and it's this way. And so this tension applies a torque. The torque is the force applied times R times the sine of the angle, which is 90. So the torque is just T times R, and it's a positive torque because it spins counterclockwise. So for the pulley, you have the torque is equal to I times alpha. The torque is R times the tension. R times the tension, that's the torque, times the sine, which is 90 degrees. Sine of 90 is 1. The moment of inertia, it's a cylinder or a disc. It's a solid disc. So the moment of inertia, you can look it up. We derived it last time. It was 1/2 mr squared. The moment of inertia is 1/2. In here, the mass is not the mass, the hanged mass. It's the mass of the pulley itself. times the radius of the pulley squared, okay, times alpha, But alpha is the acceleration over r. So I'm going to replace alpha by the acceleration over r. Because I'm after the acceleration, because we want to know how long it will take the mass to fall, so I need the acceleration. So I'm going to replace alpha by the acceleration divided by r. And you notice here, one of the r's cancels. And I have an r here and an r here, so this r cancels. So I get that the tension will equal to 1/2 of m times the acceleration. Okay, that's the second equation. Set these two equal, because the tension is this and the tension is that, so let's set them equal and get the acceleration. So we get my blue pen. These two are equal. So I get mg minus ma is equal to 1/2 of capital M times A. Move this to the other side and factor the acceleration. So you get mg will equal to m plus 1/2 of capital M times the acceleration. And so we get the acceleration will equal to mg divided by little m plus 1/2 of capital M. Let's substitute. Little m, remember, it's 2 kilograms. That's the hanged mass. G is 9.8 as usual. Little m, again, it's 2 kilograms, plus 1/2 of capital M. The pulley has a mass of what? 1 kilogram. So half of 1 is half. So you get here 2.5. Well, you calculate the acceleration. So let's calculate the acceleration. I need my calculator here. So I get 2 times 9.8 over 2.5, 2.5. I get 7.84 for the acceleration, and it's downward, the acceleration. The magnitude is 7.84, but it's in the downward direction, meters per second squared. So this is just the magnitude. Now, how long will it take it to fall? I think it says, yeah, how long? Well, I have y final equals to y. This is motion at constant acceleration, so equal to y initial plus v initial times the time minus 1/2 of the acceleration times the time squared. The minus sign because the acceleration is in the downward direction. Y final is 0, y initial is 1 meter, v initial is 0, so this is a 0, and then here plus or minus is minus 1/2 of 7.84 t squared. You move the 1 to the other side, it becomes negative. Both sides are negative, and so you solve for t. It's positive. So t will be 2 over 7.84 square root, and we get approximately 0.5. About 0.5 seconds, or maybe exactly, because things will cancel. So that's that. All right. So here we're rotating about a fixed axis. Notice, right? The pulley just rotates. It does not translate. It doesn't do this, rotate and go. Right? It doesn't roll and go. We will do that right after we do static equilibrium, which is the next topic. So the next topic is static equilibrium, and so let me write it down. Static equilibrium. What does it take to keep something like a structure, like a building, for just sitting still? Like, for example, for me to just sit still like this. So I'm not moving. For example, here is a typical thing would be like a ladder, right? You put a ladder against the wall and you want the ladder to stay in static equilibrium. What does it take for it to just sit in static equilibrium? This is the ladder. That's the ladder. What does it take? Well, you have to make sure that it doesn't move. It does not translate, what we say translate. So it does not translate, meaning the net force has to be 0 to ensure that the center of mass does not move. So we need, to stay in static equilibrium, we need the following. The net force equal to 0. So that the center of mass doesn't move. So let's say here's the center of mass. That's not enough. The center of mass may be fixed, doesn't move. The net force is 0, so here is the center of mass, it doesn't move. But it could still rotate about the center of mass. So what do I need to ensure that no rotation can start? I need to ensure that, because how do you cause rotation? Well, to start rotating, it means you have an angular acceleration. And to have an angular acceleration, it means there is a net torque, because Newton's second law for rotational motion was the net torque equals to I alpha. If alpha is 0, it means the net torque is 0, so we require that the net torque also has to be 0. So we need also the net torque to be 0. I'll put a vector here, because the torque, you will account for it either counterclockwise or clockwise torques. They have to add up to 0. And so we will do a few examples on these. All right, so we have an example here of two people. Adrienne is 50 kilograms, and she stands here. Bo is 90 kilograms and starts walking to the right. And he can walk somewhere. It says here they're standing on a 100 kilogram plank. So this thing is 100 kilograms. And it's resting on the supports shown. As you can imagine, Bo, who is 90 kilograms, so is heavier than 50 kilograms, if he walks somewhere, this might tip over. It might start tipping over. So it will start to lose contact here. So it just tips like that. So the question is, how far can he walk? How far will he be from her in order, and then it still doesn't tip, or barely tips. It starts to tip. If he goes beyond, it will tip. If he goes back, then they're fine. As you can imagine, if he stands, so if both of them stand here, then they're fine. But somewhere here, it gets dangerous, and they might tip. Let's try to figure how that works. First of all, they gave us these distances here. So the plank is how many meters long? So this is 2, this is 3, and this is 4. So that's 9 meters. So the halfway will be the center of mass of the plank here, because it's uniformly rigid and it's 100 kilograms. So at 4.5 meters, so somewhere here is the center of mass, and that's mg. Let me call it capital mass G. So what are the forces on the plank? Well, there is the force of Adrienne, because, why is that? Well, Adrienne gets pulled by gravity, and she gets pushed by the normal force from the plank, so she pushes back on the normal force of the plank, and that's equal to just her weight, which is the mg. So that's the mass of Adrienne times gravity here. And then there is the normal force from the support here, the force from the left support. And then there is the mg here, and then there is the force from the right support, right? The force from the right support. And then there is the force from Bo here, which is his mass times gravity, the mass of Bo times gravity. So you get 5 forces. Yeah, 5 forces on this plank, and we want it to stay in equilibrium. We would like it to stay in equilibrium. So for it to stay in equilibrium, the net force has to be 0. So the first requirement is that the net force is equal to 0. Well, we have 1 force down, 2 forces down, 3 forces down, and 2 up. So the net force has to be 0, and so that means net force is 0. So here, no need even for the vector, because it's just in the y direction. We only have one dimension here. We don't even have the x direction. So we need the force from the left support plus the force from the right support, both are upward, minus MAG, minus capital MG, the plank, mass G, and then minus MB times G. They have to equal to 0. That's the first one. Now we need to calculate the torques. But assume this, what's his name? Bo has walked somewhere here and it's about to tip over. What would this force be when it's about to tip over? If both stand in the middle, the supports will be carrying all of their weight. But if it's about to lose contact, it means the force is arbitrarily close to 0 if they're about to lose contact. That means the force from the left support, it will be 0 if it's about to tip. So if that's the condition, so we conclude that the force from the left support is 0, and therefore the force from the right support will equal to these. Right? If it's about to lose contact, the force from the left support will equal to 0, and therefore the force from the right support will be what? Well, it will be MA plus MA plus capital M plus MB, the whole thing times gravity. Let's calculate it. MA is 50, 100, and 90. So that's 100 plus 90, 190 plus 50, that's 240. So 240 times G times gravity. That's the force from the right support. And now we need to calculate the net torque. So that's the force from the right support if you're interested. So now let's use the net torque to be 0 for it so it doesn't rotate. So the torque, we have 5 torques to calculate. There is the torque due to Adrian. And to calculate the torque, we have to choose a pivot point, a point of rotation. You can choose your point of rotation anywhere you like. Well, there is no rotation. So I'm going to choose this because it's about to rotate about this point for a reason. Because in fact, it will just eliminate that. I will tell you why that is the case. So let's choose this to be the point of support, the point of rotation. So there is torque due to Adrian here. Her force and R are perpendicular to each other, so the sine of the angle, all of them are perpendicular, so I'll just ignore. The sine of 90 is 1. Now her torque is counterclockwise. She's trying to rotate the plank about this point counterclockwise, right? Imagine you have a meter stick, you support it here. She's standing on this side, so she's trying to rotate it counterclockwise. So the torque due to her will be her distance from this point, which is which is this, 3 plus 2, which is 5, times her force, which is her mass times gravity. So that will be 5 times her mass. What did we say? It was 50, so that's 250 G. That's her torque, and it's positive. Let's see what the torque due to the support, the left support. It will be the distance from the left support to the right support, because we're calculating the torque from here. So it would be the force from the left support times this distance times the sine of 90 degrees, which is 1. But the force from the left support is 0 because it's about to lose contact. So that's a 0. So that torque is simply 0. The torque due to the weight of the plank itself, the center of mass, well, that's counterclockwise because again, here is the support and mg is this way, so it's trying to rotate it counterclockwise. So the torque due to capital mg will be the distance from the mg to here. Well, how far is it? We said mg is, the whole thing is 9, so the mg is at 4.5. If this is 4, and the distance from here to here is 4.5, so this distance is just half. So it will be 0.5 times mg. And m is 100 kilograms, so 0.5 times 100 is 50, so that's 50 g. the torque. Of course, the units are Newton meters. And then the torque due to the support from the right, that's a 0. Why? That's why I chose it there. The reason is, remember, torque is the distance from the force to the point of rotation times the force itself times the sine of the angle. But here, the point of rotation, we chose it to be here, just a choice we made. And it's a smart choice to do it here. It's a good choice because you eliminate this. And the reason you eliminate it is the distance from the force to itself is 0, so that contributes nothing to the torque. Which makes sense. If the force is here, that doesn't contribute anything to the torque. To rotate something, remember you have to apply a force at a distance from the point of rotation. So that contributes nothing. And finally, this torque here. The torque due to B, that's clockwise, right? Because this is the point of rotation and bow is trying to rotate it clockwise. So that's clockwise, so that's a negative torque. And it's the distance from bow to here to here. I'm just going to call it R bow. I don't know how much it is. That's what we're trying to calculate. That's R bow times the weight of bow, which is mg. mb times g. So that's minus 90 kilograms, so 90 RB times gravity. And now we're going to say the net torque has to equal to 0 because it's not rotating yet. It's about to rotate. If it takes one more step here, it will rotate, but it's not rotating yet. So we say the net torque is equal to I alpha, but that's 0. So we get the net torque will be tau due to A plus L mg RB. So for this one, that's positive 250 G plus 0 plus 50 G plus 0 and then minus 90 RBG equals to 0. The G just goes away. Take the 90 RB to the other side, so you have 90 RB equals to 250 plus 50, that's 300. 300, not 30. And so you get RB will be 30 over 9 over 9. And 30 over 9 is, let me calculate it. Over 9, that gives me 3.333. So let's say 3 meters. So both is here. This is 3.3, but they want the distance from here all the way to here. Well, this is that's 5 plus 3.33, and that gives me 8.33. 8.33. Hopefully I didn't make any errors. Actually, they didn't want that. They just wanted from how far to the right of the right support. So if he is 3.3 meters to the right of this one, that's 3.33. Anyways, so from the left it's 8.33. From this support it's 6.33, and so on and so forth. So that's that. But this one, everything was linear. Let's do a ladder problem when something is curved. Well, I think I ran out of time, so I need to do it in the next video. So see you in a moment.